are in lesson 1.5, solving equations in one variable that contain more than one step. They have, more than one step to solve them. We may have to do some simplifying. We may have variable terms on both sides. That's what we've been dealing with in this lesson. So now, today we're going to come across these other situations of, well, what happens if we don't have just one solution? So we're going to start out by saying, first of all, some equations have infinitely many solutions. Oh, I need to calibrate, and I got to stop and do that. So infinitely many solutions and are called an identity. So we're first going to deal with what happens when we have infinitely many solutions. Okay. I just don't have room. I can't get this slide over. I wrote, with it being uncalibrated, I used up too much of my line. Okay. So some equations have infinitely many solutions. That means we said there's so many of them we can't list them. And that's the case. We call that equation an identity. So when we have an equation like that, we call it an identity. And I think you'll understand better why that name after we start taking a look at some. Okay, so look at our number one. It's going to be our first move in this one, just like it always is. Change subtraction to add the opposite. So let's go ahead and get that done. So get just the subtractions changed to add the opposite. We leave the additions alone. We don't need to mess with them. Okay. What should we do now? What's next? We have some like terms on the left side. What are the like terms on the left side? The -1 and the 6. Okay, so when they're on the same side, we just bring them together. What is 6 plus -1? 5. Okay, so that becomes 5. We bring along our tag along that's in between them. Okay. How about the right side? Is there any simplifying to do on that side? Any like terms? Okay, so what are like terms on the right side? Okay, the 4x and the -6x are like terms. Okay, so what does that combine to be? What's 4x plus -6? 4x plus -6x. -2x. Thanks, Calvin, for raising your hand. -2x. And then we have some constants that can be put together. We have an 8 that can be put together with a -3. So what does that become? 8 plus -3. Devante, what's that? What's 8 plus -3? 5. 5. Okay. Okay, I want to do something with that left side. I'm going to have those, because it's addition, they can trade places, can't they? I'm going to let the x's trade places with the 5. Just for the fun of it. They can. There's a property called commutative property that says add them in any order you want. So we can trade those up. And then the other side is -2x plus 5. So what's going on here? Both sides are what? Are the same. Well, whenever that happens, when both sides end up exactly the same, that's when we stop and say, you know what, this is an identity. Think of a set of identical twins. Identical twins, what's true? When they're identical twins, typically what's the case? They look the same, you can't tell them apart. Do you know any identical twins in this building that it's really hard to tell them apart? Yeah? No, who?
The Smith brothers.
The Smith brothers,
And
yeah.
I have two brothers that are twins.
You have brothers that are twins, are they identical twins also?
Yeah,
Are they hard to tell apart?
sometimes.
Yeah. And you live with them, right?
Yeah.
Yeah. So sometimes, and if we don't live with them and we see somebody on the street and, you know, they're an identical twin to somebody, we're like, hi! And then you always call them by the wrong name. It's like, oh, I'm sorry, you're the other one. I finally figured out something with the Smith brothers because I have them in class, both of them, in the same classroom at the same time. I have figured out something that I can tell them apart now, and it has to do with classes. I mean, you have to find something that'll help you. About 5 years ago, I think it was, I had triplets, identical triplets, and tried to keep them, figured out. That was not, I was never successful with that one, never worked. Okay, so called them identity because they look exactly the same, okay? And any number can make that equation true. In other words, if you pick any number you want from the number line, you just pick a number and you put it into that equation, it will make it true. So I want you to just mentally right now pick a number that you want x to be, since it can be any number you want. Okay, so what did you pick, Aurora? 10. Okay, let's put 10 in. Negative 2 times 10 is?
-20.
Negative 20. Negative 20 plus 5 is?
25. -25.
Negative 15.
Negative 10. Negative 20 plus 5 is?
Oh,
Negative 15. Well, isn't that what's going to happen on the other side too?
yes.
Negative 15 equals negative 15, true or false?
True.
True. Okay. Tell me what number you picked, Tori. 5. Okay. Negative 2 times 5.
-10.
Negative 10. Negative 10 plus 5. Negative 10 plus 5.
-5.
Negative 5. Isn't that what's going to happen on the other side too?
Yes.
So does anybody in here think they have a number that they came up with that's not going to work? Because we want to try it for you. Anybody have a number? Because you came up with one. We're going to call you a genius. Devontae.
7.
7. Okay, let's try 7. Negative 2 times 7 is?
Negative 14.
Negative 14. Negative 14 plus 5 is?
Negative 9.
Negative 14 plus 5 is what? I think you were right.
Negative 9.
Negative 9. Negative 9. Well, if we did that over here, wouldn't we get the same thing? Negative 9? Negative 9 equals negative 9? Sorry, Devontae, that one works. Oh, 0. See, 0 works? No? Let's try it then. Okay. Negative 2 times 0.
0. Wait, negative.
Negative 2 times 0.
0.
0. 0 plus 5.
5.
5. Wouldn't we get that on the other side too? Huh. Well, so now we've tried some positive numbers. We've tried 0. Maybe it's a negative number. Maybe some of the negative numbers don't work. Give me a negative number, Abby. Negative 5. Okay, let's try negative 5. Negative 2 times negative 5.
Positive 10.
Positive 10. Positive 10 plus 5.
15.
15. Huh, isn't that what we get on the other side too? Huh. Seems like a negative number works also. So we could stand here all day. We could take numbers up there at negative 1 billion. We could take a positive 1 trillion. We could try numbers all day long and they would all work. The whole number line would work. Any number can make the equation true. So we're going to say this one has infinitely many solutions. And that's how we have to state it. Okay? So once we get the equation to something like this, where we have one side matches the other, it's called an identity. That means, you know what? Any number from the number line, any real number, will make that equation true. So the solution is, you have to state the solution still. You would say infinitely many solutions. Okay. Then we have some equations have no solutions. What would happen if there's no solutions, I wonder? Okay, let's find out here. What are we going to do? What's our first move in the number 2? First move. Kelvin, what's our first move?
Change the, add the opposite.
Yep, change subtraction to add the opposite. Okay, so go ahead and do that. And maybe even insert a 1 in front of that x on the other side. Okay. Okay, are we ready to go to work solving it? Okay, why not? What do we gotta do? Oh, we got some like terms to combine on which side? Oh, both sides, okay. Well, what do we got, what are like terms on the left side? Okay, the 8x and the negative 9x. Okay. What do those combine to become, Noah? What's 8x plus a negative 9x?
Negative 1x.
Okay, negative 1x. Does that 6 have anybody to be combined, anything to be combined with? No, so it's a tag along that'll just come down. Okay, how about the other side? Any like terms on the other side?
2 and negative 15.
Okay, the 2 and the negative 15, okay. So anybody want to tell us what that becomes? It's 2
Negative
plus
13.
negative 13 plus negative 1x, okay. So what I'm going to do is I'm going to have, typically in expressions we like the variable term to be first. So I'm going to leave the left side as it is, and I'm going to have on the right side, I'm going to have those two trade places. Because I might be starting to think for a moment here, hey, they both have a negative 1x on them. Maybe this is an identity. No? Why not?
Because one side has plus a positive 6 and the other side has a negative 13.
Yeah, so the negative 1x's match up, they're identical to each other, but 6 is not the same as negative 13, is it? So this one's not an identity. Okay, this one's not an identity. So maybe we should make that little note in here, just to make sure that we don't kind of let our brain do this. As soon as we see that we have the same variable terms, we're going to say, oh, it's an identity, and stop and say infinitely many solutions. Because that's not how we can let our brain go. If we get introduced to a new thing, doesn't mean it's going to take over the world, okay? So this is not an identity, so we're going to keep going. What would we do typically now? What would be our next move? Are we ready to solve this? Yeah, what would we do? Add 1x to both sides. Okay, let's do that. Add 1x to both sides. What's the left side read now? What do we have on the left side? 6 is out here. 6. Okay. So we got 6 over here. What do we have on the right side now? Negative 13. Some of you are like, I don't want to answer because I can't figure out what happened here. What happened? Did the variable terms disappear? Do we have any variable terms left? They're gone, aren't they? So let's just state it like this. There are no x's left. There are no x's left. They're gone. They disappeared on us. And the resulting statement is,
Solution.
no, read that. What does it say? 6 equals negative 13. How do you feel about that? It is a problem or not a problem?
Not a problem.
Not a problem. Okay, 6 can equal negative 13. Okay, here's the deal. Julia, I'm going to give you $6. Cody, you're going to give me $13. All is fair in love and war. Everything's good. We're doing the same thing. You give me 13, I'm going to give you 6. Okay? Is that the same thing? You feel pretty good about that? You're not going to say, Joe, well, wait a minute. Why does Julia get money, but yet you're making me give you money? So in other words, is 6 the same as negative 13?
No.
No. So that statement is what?
Solution.
That's a false statement. There is a problem here. That is a problem. Yeah, this is false. 6 and negative 13 don't hang out at the same place on the number line. No way. 6 equal to negative 13 is a false statement. So we're going to say the resulting statement is false. So we have these two things that we're going to look for. If the x's disappear, or the a's, or the w's, or whatever the variable is in the problem, if they disappear, they're no longer there, and the resulting statement is false, then you get to come to this conclusion. There aren't any numbers that can make the equation true. There's nothing I could put in there that would make this true, so the answer is no solution. This is when it would be no solution. It's not an identity. The x's disappear. All of a sudden I'm trying to solve for x and they're no longer there. I get a statement that doesn't make any sense. 6 equals negative 13, or 0 equals 10, or negative 1 equals 1,000. It's not true. It's false. I'm going to say, you know what? This is one of those no solution ones then. Okay? So, is this what's going to happen all the time now? Infinitely many solutions or no solution? Is that what's going to happen every single time? No. It can happen along with our getting a solution, one solution. It can happen, but it doesn't mean it's going to happen all the time. Okay, let's go to the back side. We're going to do an application problem from this lesson yet. Okay, we got Marlo, who wants to rent a bike. Well, Green Lake Park has an entrance fee of $8, and they charge $2 per hour for bike rentals. Oak Park, so it sounds like there's another option. Oak Park has an entrance fee of $2 and charges $5 per hour for bike rentals. Well, Marlo, it's a he, wants to know when the cost will be equal. Okay? What are we going to do? How are we going to figure out when the costs are going to be equal? You guys can check for a while, or? I bet we could set up an equation, since we're in algebra class and we've learned how to solve algebraically. Maybe we could write an equation that we could say, oh, the cost for Green Lake Park, fill in these blanks please. This is like setting up an equation in words. Green Lake Park's cost has to be equal to, it said, wants to know when the costs will be equal. The other one is Oak Park. So when will their costs be equal to each other? Well, what do you think is the unknown in this problem? What is it that what is it that can vary? What is it that can change? Cody?
The dollars per hour.
The dollars per hour, okay, so it says Green Lake Park has an entrance fee of $8 and they charge $2 per hour for bike rentals. Does it say if you're under 5? Does it say if you have brown hair? Does it say if you come before noon? It just says they charge $2 an hour, so can that vary? It's $2 an hour no matter what, no matter the color of your hair, no matter what time of the day it is, no matter how old you are. Devontae?
X could be how long you rent the bikes for.
Yeah, you get to choose how long you want to rent the bike for, don't you? You don't get to choose how much they're going to charge you, but you get to choose how many hours you're going to rent the bike for. So I think that's our unknown in this. So let X be the number of hours, because it's per hour. So we don't just say time, we be specific. We know that they're going to charge us by the hour. So X is going to be the number of hours. That's our unknown. So that's what we do in step 1 with our application problems. We pick a variable and describe it. Okay. Anybody remember what we do in step 2 of our, when we're doing our word problems? Write down the equation. Yeah. So let's go up here and let's kind of like circle the things that are important in here. See if all numbers are important or if there's some that are not even relevant to the problem itself. So Green Lake Park, I keep wanting to say Lark. Green Lake Park has an entrance fee of $8. Is that important?
Yes.
How many times do you pay that? Once. Okay. So one time. And charges $2 per hour for bike rentals. Is that important?
Yes.
Okay, $2 per hour. Let's circle that. Anybody think they know how we could express that algebraically? $2 per hour, Cody?
8 plus 2x.
Okay, I'm just talking about this part right here. So this could be 2x, I think that's what you're saying, right? Okay. And then it moves up. So it looks like we're ready to do this side of the equation right here. So we're going to do what Cody just said. We're going to do 8 plus 2x equals. Well, now we need Oak Park's cost, so let's see what that one has to say. Oak Park has an entrance fee of $2. Is that an important number in our problem? Okay. And how many times will we use that? Once. That's a one time. Okay. And charges $5 per hour for bike rentals. Is that important?
Yes.
Okay. Let's circle the $5 per hour. How could we show that one? Just 5? 5x, because it isn't just a one time, it's $5 for every hour. So then we're going to, and then it says there's nothing else, right? So what could be our expression that represents Oak Park's costs?
2 plus 5x.
2, the one-time fee, plus the 5x. Okay. So we have our equation. Step 3 is we're going to solve it. And then last but not least, we'll write a sentence. And then we'll also answer part B here. Okay, number 3 then, solving our equation. Is it ready to solve or do we need to simplify?
Solve.
This one's ready to solve? You all agree? Okay, what should we do? Who wants to call the first step? Noah.
Subtract the 2 from both sides.
This
From
2?
8, yeah.
Okay, you want to do the 2. You want to move the 2 first. Okay, I'll let you make that call. Whatever. Okay. I think some of you would have made a different call, but we'll go with Noah. See what happens. Okay, so what's it going to read now? What's the equation going to read now?
6 plus 2.
6 plus 2x equals, these guys cancel out, and we have 5x. Okay. What would be a good next move then, now that Noah kind of started this way?
Subtract 2x.
Subtract 2x. Let's get the x's moved that have the constant with them. So we'll subtract 2x from both sides. And now what does our equation read?
6 equals 3x.
Okay, so these guys take care of each other. 6 equals 3x. Oh, we all got to make the same last move here. What's that going to be? Divide.
3.
Divide 3. Huh.
Divide both sides by 3.
Got it. You guys are getting there. 6 divided by 3, 3x divided by 3, divide 3. I don't even know what that means. Okay, and 6 divided by 3 is?
2.
2. And 3x divided by 3 is?
1.
Is it 1x or x? No, it's not 0. 3 divided by 3 is 1. So it's a 1x. So it's an x. Okay, so x equals 2. Okay, well, what does that tell us? What were they asking us to find? Go back up and see what did they want us to find.
When the cost will equal.
When the cost will be equal. When? So what did we just find?
How many hours?
We found how many hours. And so we would say the cost will be the same for, okay, the cost will be the same. Sentence. When they rent it, when he, it's a he, it's Marlowe, isn't it? Okay. When Marlowe, we'll just use his name. When Marlowe rents for 2 hours. So if he wants to go on a 2-hour bike ride, doesn't matter which place he goes? No, doesn't matter which one. Okay, what would that cost be? What are we going to do to figure that out? What would that cost be? It's the same.
Take 5 times 2.
Okay.
For the $5 per hour.
So in other words, we could use, so you're using the $5 per hour. Are we going to have to do anything other than multiply by 2? Is there any other cost at that part?
Multiply 8 by 2.
Do we have to take the 8 times the 2? What do you think, guys?
Yes. Or no, you had to add 8 to what you get.
I thought the cost at Green Lake Park was 8 plus 5x. Am I right? And then, or in reality, we only need to use one side of the equation or the other, because that's when they are the same. So we could use, what was the other one? What was Oak Park?
2 plus 5x.
Really?
The first one should be 2x.
Oh, the first one should be 2x. That's what I was like, I don't think they can be the same here. Okay. Otherwise, we would have a no solution one. So we got that one. This is Oak Lake Park. And this one is, or Green Lake Park. I'm calling it the wrong thing. Green Lake Park. And this is Oak. Is it just Oak Park, or do they have another name in theirs? Oak Park. Okay. So it doesn't matter which one you use. Use one of them. Substitute in your 2. So we have 8 plus 2 times 2. If we're using that one over here, if you're using this one, it's 2 plus 5 times 2.
Cost.
Okay, so let's write another sentence. What did you find out? What did you find out? Anything?
There's very many solutions.
There's infinitely many solutions. No, I don't think so. Not for when they'll be the same. Cody?
The cost of both parts is $12.
Okay, the cost at both parks for 2 hours for 2 hours, that's what we were doing it for. When would it be the same? This is the only time it would be the same. The cost at both parks for 2 hours is $12. There's not another number of hours that they would both exactly be the same. This is a one solution one, not an infinitely many. This is a one solution one, okay? Okay, let's be done.